Namaskara. In this session, we begin our discussions on amortized analysis of data structures. Amortized analysis. This is an interesting way of analyzing the performance of a data structure. We design a data structure to carry out certain operations efficiently. So, we have an abstract data type, it has got mathematical objects and you have operations on them. These mathematical objects are to be represented, we need a data structure for that, and those operations are to be performed on the data structure. Now, we are designing the data structure in such a way that the operations are performed in an optimal way or in a very efficient manner. Our typical design of a data structure would focus on the worst case complexity of each operation. So, we design data structures that would minimize the worst case cost of operations. The worst case cost of operations. And this imposes certain constraint on the data structure. Okay, this makes the data structure design a little more complicated, or we need to have a lot of bookkeeping information and we have to do some more restructuring mechanisms. All of them we may have to do in order to achieve the bounds on the worst case cost of operations. Okay? We are going to relax this. We are not going to focus on the worst case. However, we are interested in optimizing or minimizing the total cost of performing several operations, a number of operations. Okay. So, let us say we have a data structure. You can imagine for instance the binary search tree, okay, balanced binary search tree, We perform the operation of insert, delete and search or membership problem. All of them it takes order log n time. Okay, all of them take order log n time in the worst case. So, the design either AVL tree or red black tree, you might have seen that they are fairly sophisticated and complicated. The routines handling the deletion are all fairly complex. In order to achieve this bound of order log n, a lot of efforts have been put in the design as well as in the implementation part of the data structure. Okay. So, if you perform a sequence of n operations, let us say O1, O2, O3, ON, you are doing n operations. It can be an arbitrary mix of this operation. O1 could be insert, O2 could be insert, O3 could be delete, O4 can be search. All of it's an arbitrary mix of n operations. Because of the worst case bound that we have, we can say that the total cost of this n operation, whatever is the operation that you do, the total cost is upper bound by n log n. The total cost is upper bound by n log n. Now, I am not interested in bounding the cost of each operation. I want to make sure that the total cost is n log n. Okay. Therefore, I do not have this kind of a bound O1 less than or equal to log n, O2 less than or equal to log n, On less than or equal to log n. That is the reason why the total cost is order n log n here in balanced binary search tree. But we are going to look at a new data structure called the display trees, in which the operations at any given time may take arbitrarily large amount of time. It could take even order n time, some of the operations, but the total is bound by n log n. Therefore, without worrying to optimize the cost of each operation, you can come up with a data structure, okay, and make sure that the total cost of n operation is upper bound by n log n. Therefore, it will give competitive performance. The total cost of any set of operation will be of the same order. However, the constraint that each operation must be done in an optimal way is removed, and that relaxation allows us to design simple data structures and do the things in a more efficient way, in a simpler way. Okay. When there is no specific bound on each operation like this, how are you going to measure the total cost of n operation? There is absolutely no decent bound. Okay. So, for example, if I have operation 1, operation 2, etc., operation n, the actual cost of this is C1, C2, let us say Cn. We are interested in getting a bound for C1 plus C2 plus Cn. This is the actual cost. But now the actual cost does not have any uniform bound. It can be arbitrarily varying. Some of them could be very cheap, some of them could be very expensive. All I want is that I want this cost to be less than or equal to, let us say, n log n. But I am not bounding each one of them. In other words, there may be one expensive operation. In a compensating manner, I will have a lot of very cheap or low cost operation. So, it will average out to n log n. Okay. That is how the data structure should be designed in such a way that it is averaging out. So, for every costly operation, if you have several cheap operation, the total cost will be controlled. That is what we are aiming at. Okay. But then if the costs are arbitrarily varying and it depends on the operation sequence and everything, how are we going to prove mathematically the bound for this? C1 plus C2, C1 and C2 do not have individually any decent bound. Their costs are arbitrary numbers, and I want to bound these C1 plus C2 plus Cn. That is mathematically challenging. So, this is where an ingenious technique is evolved, and that is called amortized analysis. In amortized analysis, we are going to mathematically create some entities purely for the sake of analysis, and they are called amortized cost. Okay. This is created purely for the sake of analysis. Okay. So, I am going to create n numbers A1, A2, etc., An, such that C1 plus C2 plus Cn is less than or equal to A1 plus A2 plus An, but these numbers A1, A2, An are all standard numbers, are simple one, so that this sum is easy to compute. This sum is complicated to compute because the actual costs are wildly fluctuating. I am not giving any bound on the cost of any operation. So, it could be fluctuating and wildly varying, but these wildly varying costs are bounded by a set of numbers that I am going to define, and these are called amortized cost. It is in some sense averaging out. So amortization means averaging, but we do not want to use the term average. It is not actually average. It is not the sum of the cost divided by the total number or something like that. It is not like that. It's the concept is, although it is kind of averaging, it is different, therefore the creators have named it in a different way. It is called amortized cost. Okay. This property is needed. There are two properties that you want to have for A1 to AN. A1 plus A2 plus AN must be an upper bound for this. But if A1 plus A2 AN is also equally messy, complicated, and mathematically you cannot simplify that, then there is no point in creating those A1 to AN. My problem is I want to get C1 plus C2 plus Cn in a compact and in a good bound I want to get, and these A1 to AN must help in that. If you simply define some numbers which are acting as an upper bound, and if you can't even simplify that sum, it's not taking you anywhere. Therefore, ingenuity lies in coming up with the right amortized cost and then carrying out the analysis. Therefore, this is basically a mathematical technique to analyze the performance of a data structure. So, a new data structure will be proposed. On that we will carry out the operation, but what will be the total cost? We are not going to look into the individual cost of the operation. We are going to analyze the total cost of performing n operations in a data structure. Okay. So, we are going to let me illustrate that with an example, and these introductory concepts are very essential to understand, because this is what we are going to use for split trees and later on Fibonacci heaps, and it is a Fibonacci heaps that we are going to use for implementing the Prim's algorithm that we have looked at. So, it is a long chain of discussions finally leading to the implementation of minimum spanning tree algorithm and Dijkstra's algorithm and so on. Okay. All of them require the mathematical tools related to amortized analysis of data structures. Okay. So, let us take a very simple example to understand what is amortized analysis, how the amortized costs are coming into picture, and how they are helpful in getting the bounds for actual cost. So, this is the actual costs. These are called amortized cost. Amortized cost of the operations. So, let us look at the following example. Consider a stack with the following extension of the operation. Okay. Push x s. This will push x into the stack. Push x over the stack yes. So, whatever is yes, one more item, it will be in the top of the stack. Push x. Now, instead of pop, which is going to throw only the top item, I am going to define m pop. M pop the stack yes, and k, that is you are going to throw k elements from the top. The top k elements will be removed from yes. The top k elements will be thrown out. Okay. Of course, there should be k elements. If there are no k elements, whatever is the number of elements in S, that will be thrown out, and when S becomes empty, you stop. Therefore, this command can be given for any integer, but its actual cost, right? Its actual cost. What is the actual cost? The actual cost of this one is like this: minimum of cardinality of S and K, whatever is the number of elements in S and K. For example, M pop S10, if cardinality of S is 20, there are 20 elements, you have to throw 10 elements out. In each operation in each step you throw one element. Therefore, if S equal to 20, the cost, actual cost will be 10. If cardinality of S equal to 5, you may give this command, throw 10 items, but S has got only 5 items. So after those 5 items are thrown, the process will stop. There is no more element to throw out. Though you have given this command, its cost is going to be only 5. That is the reason why it is the minimum of, here the minimum of 20 and 10, here the minimum of 5 and 10. So it is a minimum of cardinality of S and K. This is the actual cost of M pop. But this can be order n. Okay. For example, you may say push, push, push and so on n by 2 times, and then you can give multi pop S n by 4. So n by 4 elements are to be thrown out. So n by 2 elements have walked in, n by 4 elements have gone out. So in the worst case, the actual cost in the worst case can be as high as order n. It could be, it depends on how many elements are in S and what is the value of K and so on. But that is arbitrary, it can be arbitrarily large. So in any sequence of n operations, the M pop may be order n. Okay. For example, the first n by 2 operations, the first n by 2 operations can be push x1 S. Initially S may be empty, push x1 S, push x2 S, push let us say x n by 2 S. N by 2 operations you have done. I am looking into a sequence of n operations. Each push is 1 because you have to put the element in the top, that is all. So each push has got actual cost 1. The actual cost of now M pop S n by 4 or even n by 2, you can have even n by 2. This is order n, okay, and so on. I can continue with some more operations. So I can have an arbitrary sequence of operations. Let us say I start from S equal to empty, I perform operation 1, so this is called S0. I perform operation 1, then I have the data structure S1, I perform O2 and I have the structure S2. This is a stack configuration. For example, S1 is a stack containing only X1, S2 is, if this is O2, X1 is there on the top, you have S2, that is S2, the data structure, the current configuration of the data structure after performing the operation. Then when you do O3, you get S3, and in this way ON you have Sn. The data structure configuration keep changing with every operation, it will change. Okay. So the actual cost C1, C2, C3, Cn. What can I say about C1? I do not know. It could be anything. It could be an M pop, it could be a push C2. And for example, here this operation is order n. So some of them could be order n. The actual costs are wildly fluctuating. So if you, the only information you have is any operation is order n. It's a 1 or it could be order n. If you use that bound, each operation is bounded by order n, there are n operation, therefore this is C1 plus C2 plus Cn is less than or equal to some order n square. You can say that right now, but this is a very weak upper bound, very large bound. The actual costs are adding up to a very small number, but we didn't study the fluctuation carefully simply because we don't know anything about the actual costs. We thought let us have the worst case scenario order n, then put order n bound for everybody and get order n square. That's a very bad analysis. It doesn't lead to. So here I am going to introduce the amortized analysis. There are two styles in which we can carry out the amortized analysis. Okay. So one is called kind of a banker's method. Another one has drawn inspiration from physicists, so it's called the potential method. Okay. The bankers or accountants method or potential method. Let us say the accountants method. Okay. So imagine the thought experiment. Okay. For each operation that you perform, you are going to get 1 rupee. I am going to ask you to perform the operations, and for each operation you are going to charge 1 rupee. Okay. Any step you do, one step if you do, you are going to get 1 rupee. So for push, your charges are 1 rupee because one step. For MPOP, your charges are k rupees, where k is the minimum of that much I have to pay. Therefore, how much you are going to get? Suppose I ask you to perform a series of operations. The total you are going to get will be total number of steps you have carried out, right. So for each operation you are going to get 1 rupee. Whatever is the total number of operations you have done, total number of steps you have carried out, that many rupees you are going to get. So the actual cost is cost of push is 1. MPOP is minimum of cardinality of S and K. Whatever you do, this much, when you execute MPOP you are going to get this much money. Okay, fair enough, that many operation you are going to do. So for performing a series of n operations, how much you are going to earn? Okay, that is going to be the upper bound for C1 plus C2 plus Cn. So here is a funny way in which I am going to pay. Okay, for push I will pay you 2 rupees. For MPOP I will pay 0 rupees. I will not pay anything for you, right. But what I am going to ask you is to do the following. Hey, I will give you for every push 2 rupees, you take your labor charge 1 rupee, save 1 rupee for future use. That is called the surplus, right. That is called surplus. So you have some surplus with you, because for every push operation I am going to give you 2 rupees. For push operation you take 1 rupee for your labor and keep the 1 rupee aside for surplus. Then I am going to say that you carry out the MPOP operation. I will not pay anything. But then you have surplus, take the money from the surplus. K rupees you are going to, you have to get K rupees, because for MPOP operation this many steps you are doing. So I have to pay you K rupees, but I am not paying you here, but I am saying that from the surplus you take, so that you are paid. You are paid for your labor. For each operation 1 rupee you will get. For MPOP also you are going to get K rupees, but that you are going to take from the surplus. Will there always be a surplus to pay for this MPOP? Because I am not paying, the surplus should be sufficient, okay. But this is what we are going to first prove, okay. The surplus is always, you are going to have this, whatever is the size of the stack, this many rupees you are going to have with you as surplus. The way in which I have paid, this much you are going to have for surplus. All right. This is interesting. Surplus you will have in your hand always this much. We will prove this. Suppose you have currently cardinality of S surplus. Suppose you are performing the push operation, push X S. So cardinality of S stack size become this. Now what happens is, for push I am giving you 2 rupees, you are taking 1 rupee and you are putting that 1 in the surplus. You already had the surplus, yes. Now you are putting 1 more rupee in the surplus, your surplus will also be cardinality of S plus 1. Stack size is this, surplus is this. So you can see that surplus is stack size. Surplus is equal to stack size. Suppose you do MPOP operation, MPOP cardinality of S K, all right. I am not going to pay you anything. So from the surplus you are going to take K rupees. Let us say cardinality of S is greater than or equal to K. Cardinality of S is greater than or equal to K. That means let us say MPOP S 10, assume that cardinality of S is 20. Therefore you have 20 rupees with you, because my surplus is stack size. You have 20 rupees surplus with you. Now I am asking you to carry out MPOP S10. So I have to pay you 10 rupees, but I am saying that take it from the surplus. So you take 10 rupee from the surplus, your labor is paid. Now your surplus is reduced from 20 to 10, because, but then the number of elements in the stack, you have MPOP. So from S you are removing 10 elements. Therefore cardinality of S is also reduced now. Okay. So cardinality of S is also reduced to 10. So now you can see the way in which the let's have cardinality of S as 15, so that the 10 there should not confuse you. Let us say cardinality of S is 15 and MPOP 10 you have given. You are taking, you have 15 rupees with you. For the labor you have taken 10 rupees away. So 15 minus 10, the surplus will be 5. Again from S you have removed 10 elements. So cardinality of S is 5. Now you can see that surplus is 5, cardinality of S is also 5. So you can do any operation, you will always have a surplus which is cardinality of S, which is cardinality of S. Because you have cardinality of S surplus, you can carry out this operation always, because it is the minimum of cardinality of S and K. If K is smaller, that much you will get. If cardinality of S is smaller, everything you will take, all the surplus you will take towards your labor, because you have emptied the stack. Fine, you will always be paid. So, how much you would have got in this process? What is the maximum you could have got? Right? You have carried out the operations O1, O2, etc., On. But what I have done is, if it is push, so let us say this is push, I have paid 2 rupees. If it is push, I have paid 2. If it is M-pop, I wouldn't have paid anything. If it is M-pop, I wouldn't have paid you anything. And if it is push 2. So the total, even if all of them are 2, it will be less than or equal to 2n. So maximum I would have given to you is 2n, of which 2n minus surplus is what you have taken, because surplus is, you don't touch that, right? You have take what is surplus? Whatever you have taken for your labor, remaining is surplus. Surplus could be 0, it could be. Therefore, your actual total of actual cost is less than or equal to 2n minus surplus. This much only you have taken for each operation that you have done, which is less than or equal to 2n. Therefore, any sequence of n operations is going to cost only 2n, maximum 2n, maximum 2n. That is all. This is the maximum. This is going to, this is an upper bound, much better than n square. This is amortized analysis. These 2 and 0 are called amortized cost. I pay you 2 rupees and then I have paid you nothing. This is my implication of my cost, right? Therefore, this is called amortized cost, the 2 and 0. So, push amortized cost is 2, M-pop amortized cost is 0. So, your actual cost of C1 plus C2 plus Cn, which will have 1s and min k and some arbitrary, it is less than or equal to 2 plus 2 plus 0 plus 0 plus 2 plus 2. Maximum, assuming all of them are 2, it is less than or equal to 2n. Now you see how comfortably I got a bound. I got a comfortable upper bound. While these quantities are messy and complex, these quantities are clean, neat, simple, and their sum I could evaluate, and it gives a much better bound. This is amortized analysis. These costs are called amortized cost. Conceptually it is introduced, and the way in which it is introduced, and then we prove that this sum is greater than or equal to this sum, and then we evaluate that sum. Okay, but how did I get 2 and 0? Looks like magic, isn't it? We will see that in the continuation of our discussion in the next session. Thank you.